look back to the early formation of the universe, and it has been doing just that. It has taken pictures of 6 galaxies that are some of the oldest we've seen, but they're a little faded. This moment takes us back to the very beginnings of the universe. The announcement from the James Webb Space Telescope, JWST, regarding what lies at the end of the observable universe has sparked unprecedented excitement and curiosity. When the JWST was launched, its mission was clear: to peer deeper into space than any scope before, unraveling the mysteries of the universe's origin, structure, and perhaps even its ultimate fate. This momentous occasion, when the telescope revealed its findings about the farthest reaches of the cosmos, marked a turning point in our understanding of the universe. For centuries, humanity has wondered about what lies beyond the stars, and now we have been given the most detailed glimpse yet into the distant frontier of space. Before we dive into the details, don't forget to hit the like and subscribe buttons for more exclusive news. The observable universe is a mind-bogglingly vast region, stretching approximately 93 billion light-years in diameter. It is the portion of the universe that we can see from Earth, limited by the speed of light and the age of the universe. As we look further into space, we are essentially looking back in time, since the light we observe from distant objects takes billions of years to reach us. The James Webb Space Telescope was designed to study these distant objects, operating in infrared wavelengths to penetrate cosmic dust and reveal ancient stars and galaxies. When the announcement came that the JWST had successfully captured data from the farthest reaches of the observable universe, it was a moment of profound significance. At the edge of the observable universe, the JWST discovered galaxies that existed when the universe was only a few 100 million years old. These galaxies are faint and distant, but their light has traveled billions of years to reach us. Their discovery represents a window into the infancy of the universe, allowing scientists to study how the first galaxies formed and evolved. The findings suggest that even in the earliest epochs of cosmic history, galaxies were forming more rapidly and in greater numbers than previously thought. This challenges existing models of galaxy formation and indicates that the early universe was far more dynamic than anyone had anticipated. One of the most fascinating aspects of these galaxies is their redshift, which refers to how much the light from an object has been stretched as it travels through the expanding universe. The higher the redshift, the farther away, and thus the older, the object is. The JWST's ability to detect galaxies with extremely high redshifts means that we are now able to observe light that was emitted shortly after the Big Bang. These galaxies, located near the edge of the observable universe, provide crucial information about the early stages of cosmic evolution. As we study these ancient structures, we gain insights into how matter began to coalesce into stars and galaxies, eventually leading to the formation of the complex universe we inhabit today. The implications of these discoveries are profound. By observing the end of the observable universe, we are essentially witnessing the universe's childhood. This era, known as the Cosmic Dawn, is a period that has long eluded detailed study due to the limitations of previous telescopes. The James Webb Space Telescope, with its advanced capabilities, is now able to shed light, both literally and figuratively, on this mysterious time in cosmic history. The galaxies detected at the edge of the observable universe are not just relics of the past. They are also key to understanding the processes that led to the formation of larger structures, like galaxy clusters, superclusters, and ultimately the large-scale structure of the universe itself. In addition to providing new insights into the formation of galaxies, the JWST's findings also raise questions about the nature of dark matter and dark energy. These two mysterious components make up the vast majority of the universe, yet they remain poorly understood. The data collected from the end of the observable universe may offer clues about how dark matter influenced the early growth of galaxies and how dark energy has driven the expansion of the universe. The universe, just a few 100 million years old, a mere fraction of its current age of 13.8 billion years, was in its infancy when these primordial galaxies were formed. These galaxies, faint and redshifted by the expansion of the universe, offer a unique window into the earliest stages of cosmic evolution, Prior to the James Webb Space Telescope, astronomers relied heavily on the Hubble Space Telescope, which gave us incredible insights into the universe. However, its capabilities were limited in terms of observing the very first galaxies and stars. The Webb telescope's ability to detect infrared light, which is stretched by the expansion of the universe, allowed it to look further back in time than ever before, capturing images and data from a time when the universe was only a few billion years old, or even less. What the JWST saw at the end of the observable universe wasn't just a few faint specks of light. It was the formation of the very first galaxies, possibly even some of the first stars. Known as population 3 stars, these stars, made entirely of hydrogen and helium, are thought to have been massive and short-lived, burning through their nuclear fuel quickly before exploding in supernovae. These explosions seeded the cosmos with heavier elements necessary for the formation of planets, life, and everything we know today. Observing these ancient stars and galaxies is critical because it helps us understand the processes that led to the development of the complex universe we inhabit now. The discovery of these ancient galaxies also raises profound questions about the structure and limits of the universe. When we talk about the end of the observable universe, it's essential to realize that it's not a physical boundary. Instead, it marks the furthest point we can see due to the finite speed of light and the expansion of the universe. Beyond this horizon, the universe likely continues, but we have no way of seeing it because the light from that distant region hasn't had enough time to reach us. The JWST's ability to push the limits of our observable universe even further opens new possibilities for understanding what lies beyond that horizon. One of the most tantalizing implications of this announcement is the insight it provides into the expansion of the universe itself. The universe has been expanding since the Big Bang, and this expansion appears to be accelerating due to a mysterious force known as dark energy. By studying galaxies at the edge of the observable universe, the JWST helps astronomers measure the rate of expansion more accurately, shedding light on the nature of dark energy and how it might evolve in the future. This has profound implications for the ultimate fate of the universe. Will the universe continue to expand forever, with galaxies drifting further and further apart until the stars burn out and space becomes a cold, dark void? Or could dark energy change over time, perhaps causing the universe to collapse back in on itself in a big crunch? These are the kinds of questions that the data from the JWST will help answer. Moreover, the JWST findings at the edge of the observable universe force us to reconsider our understanding of cosmology, particularly the idea of inflation. The rapid expansion of the universe in the moments after the Big Bang, known as inflation, suggests that the universe expanded exponentially in the first fractions of a second, smoothing out any irregularities and setting the stage for the formation of galaxies and large-scale structures. However, if the JWST finds unexpected structures or anomalies in these distant galaxies, it could challenge the inflationary model, prompting physicists to refine or even overhaul our current understanding of the universe's earliest moments. Beyond the cosmological implications, the announcement has philosophical and existential significance as well. The discovery of galaxies at the farthest reaches of the observable universe prompts us to ask fundamental questions about our place in the cosmos. What lies beyond the observable universe? Is there a multiverse with countless other universes existing beyond our own, each with its own set of physical laws and conditions? Some theories suggest that the observable universe is just one bubble in a vast multiverse, with other bubbles existing beyond the cosmic horizon. If true, this would mean that the universe we see is only a tiny part of a much larger and more complex reality. These discoveries also highlight the limits of human knowledge and the scale of the universe. As we look deeper into space, we are reminded of how small and fragile our planet is in the grand scheme of things. Yet, at the same time, the fact that we are able to observe and understand the universe to this degree is a testament to the power of human curiosity and ingenuity. The James Webb Space Telescope represents the pinnacle of decades of scientific and engineering effort, and its discoveries will shape our understanding of the cosmos for generations to come.